Welcome to the last lecture of chapter 3. So today we'll be done with this relatively short chapter, but this was very fundamental, especially for also the next chapter. It's all talking about metals. Here we talked about complexation, precipitation. In the next chapter, we're going to talk about redox of metals specifically. So the first part of precipitation and dissolution, we discuss basically KSP, the solubility product. It means we also have potential precipitation when we have metals with some of those ligands that we discussed in the first two lectures of the chapter. So in the first lecture, we mostly introduced the concept of KSP, which was like an equilibrium constant, specific designation for the productive and the solubility product. And also we mainly focus on hydroxide containing precipitates. But here we'll be expanding that to a wider range of ligands that could potentially lead to a precipitate. At the end of the lecture, more than one precipitations. And what we discussed was also an approach to do speciation, basically that minimum idea of the no precipitation scenario versus the precipitation scenario based on KSP, picking the minimum and then proceeding with the speciation as we normally do. Also, in one example here, today we're going to discuss more than one precipitations with potentially more than one, which is in this case two. And here we don't have much of the lecture, mainly three examples. So in each example, we're making it a little bit more comprehensive. But we're going to introduce a diagram in this lecture, which would be very useful for this chapter, for the following chapter as well. Because as you see, it's getting more and more comprehensive. Now you have complexation, precipitation, a little bit of acid base, then that acid base could be connected to gas liquid equilibrium. In the next chapter, also connected to a redox. So there might be a lot of equilibrium going on in the same solution. So such diagram would be extremely helpful. So we're going to introduce that today. Also use it for the three examples that we have. So specifically, we're going to solve for system with non-hydroxide precipitates, as I mentioned. Quantify three-phase system. So this time we have liquid, gas, and liquid connected to solid. And also we're going to do a PCPH diagram for more than one potential precipitates. A little bit of overview of what we talked about in the previous lecture. We specifically focus on hydroxide containing precipitates. For example, silver hydroxide is in equilibrium from the solid phase to the liquid phase. So in the aqueous plus hydroxide, also in the aqueous. And then we describe this reaction, the equilibrium using KSP, which was basically the activity, or to be a little bit more, to simplify it, concentration of the products. And this was basically at equilibrium. So we also mentioned that if we're not at equilibrium, similar to any general reaction, we introduce that reaction quotient and compare that reaction quotient with KSP. So if QSP was lower than KSP, then we are under saturated. So we still have room to add more of the metal or the ligand. But if QSP is bigger than KSP, then we are basically oversaturated. And we see precipitation. Or the ladder we used before. So the reaction progress on the right hand, this is basically KSP. If we get QSP smaller, then we have dissolution. So basically we're dissolving silver hydroxide into silver ion and hydroxide ion. And if QSP is bigger, at any moment, then we basically, to reach the equilibrium, we have precipitation. So basically, precipitation and dissolution is very similar to what we had for gas tripping and the dissolution and volatilization of the gas as well. So it's a similar analogy, like going either towards dissolution or precipitation. So far in this chapter, we started looking at the reactions of metals with different ligands in the solution, the complexation reaction specifically, and we talked about a diversity of ligands that could potentially react with a specific metal. So here I'm showing silver, which could react with carbonate, sulfate, different sulfates, and then we have the quantitative description, which was basically a log of beta, for example, in this case. So we have the quantitative information about the equilibrium. So this is what we cover in lectures 3.1 and 3.2. So what we specifically mentioned was that metal can have potential complexation with hydroxide to form metal with, for example, one hydroxide. I'm just ignoring the charge, so metal with two hydroxide and so on. Also showing metal could also complex with other ligands, so MlL1 and so on. So we had a complexation route for the metal. So in the previous lecture and also in this lecture, we're going to highlight the potential precipitation with some of the complexes, some of the ligands. So this would be what we're covering, or what we covered in lecture 3.3 and 3.4. So that means the metal can be also involved in potential complexation with hydroxide to form metal hydroxide in the solid form, also with other ligands, and so on. So this is a very simplified diagram that I just talked about. We're going to use that. And basically what it does, it simplifies or it decodes what might happen to the metal center. So we have the metal as the star of the show. We have a complexation box. We have precipitation box. Later, we're going to add more and more boxes. So it will organize your approach towards the speciation so much. So as I mentioned, we mostly cover only hydroxide precipitates in the previous lecture. Here we're going to basically expand that towards something that it's by itself has a more complex behavior environmental system. For example, carbonate. Because when we have carbonate, that means it is a part of acid-base reaction, and it could be a part of gas-liquid equilibrium. So we're adding that complexity towards something that could also precipitate. So that's basically something that we're going to cover in this lecture, and that would be basically the whole idea of this lecture. We're going to solve for 3 examples. They're different in terms of like what is included, what is not, diversity of the complexation, also where that complexing agent is coming from. So the first one is cadmium carbonate precipitate. So we know calcium carbonate is a very insoluble species in environmental systems. by just looking at the KSP is 10 to the minus 12. And the reaction associated to this precipitation is cadmium carbonate, releasing cadmium iron carbonate. So if this is the salt, these are the aqueous species. We want to construct the PC-pH diagram, considering these potential reactions for cadmium in environmental system. I know this is not all the reaction that cadmium might undergo, but this is basically what we are mainly considering for this specific example. First assumption is that cadmium carbonate is the only possible precipitate. So cadmium hydroxide we are not including. Maybe thermodynamically is not feasible, maybe kinetically is not feasible, or maybe we just want to go for like a simpler example. So the reason is just we are focusing specifically on one possible precipitate. We know cadmium can complex with up to 4 hydroxide. So we know all the calculation for that one from the first 2 lectures of the course. And we're ignoring all the other possible complexation. So we got 4 beta value, all with hydroxide, 1 KSP value, and the total concentration, the total for cadmium, the total for carbonate. So one thing about this carbonate and cadmium is that cadmium might precipitate. So we have to go with scenario of no precipitation with precipitation, similar to the previous lecture. For no precipitation, we're allowed to use total mass balance for cadmium. For carbonate, if we have precipitation, then we're losing some of the carbonate. That carbonate is leaving the system. But when we look at the relative value of the two, we see that if all the cadmium is complexing with carbonate, then that would be just 10 to the minus 2 compared to 1 mole of carbonate. So it's fair to assume that the concentration of total carbonate, it doesn't change, even though it might change, but it's not significant. Okay, so the first thing, this is the most important step, is to look at basically the diagram for the whole system. So this is what I mentioned before. First thing is we have cadmium, 2+. It will complex with up to 4 hydroxide. So that means 1 ligand, which is hydroxide, up to 4. So that means it generates up to 4 species. Cadmium OH+. Going from cadmium with hydroxide to cadmium OH+, the equilibrium constant would be beta 1 for hydroxide, and so on. Cadmium OH2. This cadmium OH2 is not a precipitate, it's basically a dissolved species. So beta 2 of hydroxide, cadmium OH3 minus, beta 3 of hydroxide, and cadmium OH4 2 minus, beta 4 of hydroxide. So this is all the potential complexation reaction for cadmium. So, and we have the information about all the equilibrium. So this would be basically the complexation reactions. So if we were in lecture 3.1 and 3.2, this would be the only possible reaction we might have, or a little bit more tails, for example, other complexation reactions. But for now, we have only these 4. So the other route for cadmium to be used is basically through precipitation. So we have only one precipitate, one potential precipitation, with carbonate to form cadmium CO3, cadmium carbonate. And this reaction, the equilibrium would be KSP for CO3. So the KSP of the reaction indicates or can be used for this reaction. So this would be the precipitation, or the precipitation possibility of cadmium. So now the other tale is that carbonate could be also a part of acid-base reaction. So this carbonate could convert to, or could be in equilibrium with bicarbonate and with carbonic acid. We know Ka2 dictates the equilibrium of the first reaction and Ka1 for the second reaction. So we're dealing with the third category, which is basically an acid base. So we use acid base kind of expression, or what we've learned for acid base for this part of, or this branch of the reaction network. The last information about the last branch, acid base. This is a closed system. So we're assuming that the carbonate concentration doesn't change based on what we talked about. It's much bigger. So this is basically the way we approach this is a closed system. Or total CO3 is fixed. Because total CO3 is much bigger than total cadmium. So even if we have precipitation, it won't change that. So the reason this kind of diagram is very useful, the first thing is it gives you all the species. So that's the first thing. For example, these are the cadmium containing species in the aqueous phase. It gives you all the reactions with their constant. So I have 4 reactions here, 5 and 3 reactions here. Also, it gives you all the possibilities that you might consume or introduce cadmium to the system. So everything is well organized. The next part is basically approaching this and then including all the reactions. So a combination of what we've learned in chapter 2 and chapter 3, the first 2 lectures, and then the third lecture of chapter 3. So to approach this, we first have the 2 scenarios. The first scenario, we assume that there is no precipitation, no precipitation, or that NP scenario we discussed in the previous lecture. In that case, we know that we're allowed to use the mass balance, so that there's no precipitation, so it would be literally a complexation approach. Based on the first 2 lectures, we know the total cadmium would be the combination of all the dissolved species of cadmium. Cadmium with 1 hydroxide, cadmium with 2, cadmium with 3, and cadmium with 4 hydroxide. That was basically a no precipitation. And based on the first 2 lectures of the chapter, we know how to calculate based on the concentration of cadmium using the beta value. And since this is a no precipitation, so we use this NP So this NP was the total cadmium divided by 1 plus beta 1 hydroxide plus beta 2 hydroxide plus beta 3 hydroxide plus beta 4. So this is something that we can easily calculate because this is a pH-dependent expression. This is a constant. This is pH-dependent. So we can quickly calculate the concentration of cadmium at non-precipitation scenario. And following, we can calculate the concentration of all the individual species based on that core calcium concentration. So this was very straightforward, and we had it before. So we mentioned in the previous lecture, we also have with precipitation scenario. So we assume that we have precipitation, or the cadmium concentration exceeds to the value that we have precipitation, and in that case, the concentration of cadmium max, we call that max because it's the maximum that we could have, is basically a KSP divided by the concentration of the ligand, in this case, carbonate. So now we have the no precipitation concentration, the max concentration. The next step was we calculate both of these two. The minimum would be the one that we can use to calculate other species concentration. But the problem with this one is that unlike this one that is directly related to pH, it's hydroxide, here we need to calculate carbonate at each pH, so one extra step. So we need to basically solve for that branch of acid base to be able to calculate cadmium 2 plus max at each pH. So to do that, to calculate the concentration of carbonate at each pH, because this is a closed system, we can quickly use alpha term. So this would be alpha 2, and we know how alpha is connected to pH. So that would be one way. The other way, we could also use the mass balance. So to somehow calculate for speciation of carbonate at a given pH. So it would be pretty straightforward. Here, for example, I'm using the mass balance of carbonate. So the total mass balance would be H2CO3 plus HCO3 minus plus CO3 2 minus. And we know what's the value. I think it was 1 molar. And we know we're dealing with basically the two reactions. H2CO3 is in equilibrium, HCO3 minus plus H plus. And then Ka1 would be HCO3 minus H plus H2CO3. And then the same thing for the second pKa. CO3 2 minus plus H plus, then Ka2, CO3 2 minus H plus, HCO3 minus. Again, this can be easily solved by alpha, but here we're just expanding this because we're assuming, because later this would be a better approach, because you might have complexation reaction involving carbonate. If that's the case, you have this mass balance extended a little bit. You see that later. So if we combine 1 and 2, rearrange it, and putting into mass balance of CO3, Then we get CO3 2 minus to be a function of pH and other constants. Total CO3 is a constant. Then 1 plus H plus Ka1 plus H plus 2 Ka1 Ka2. And then basically we use this for cadmium 2 plus max calculation. So again, what we did was the no precipitation, all based on what we've learned in the first 2 lectures of the chapter, just a complexation using beta. And if you do that, this would be what you get for cadmium concentration. With precipitation, it's very straightforward. It's actually very similar to the Henry's law, the HPM or the P. So this is a similar analogy here. This is the max we could have in the system, because beyond that, the concentration would be fixed, but then starts to precipitate. In this case, this is not directly, the pH dependency is not very obvious, so we need to convert this one into a pH dependent variable, which we did here. So what we do is basically at each pH, we calculate this guy, we put it here, we calculate this guy. We already calculated this one based on pH, then we compare the two as we did before. So that means at each pH, what we do is we calculate both cadmium 2 plus from no precipitation scenario and cadmium 2 plus max. And then we take the minimum and that would be the concentration of the cadmium 2 plus. And then once we have the cadmium 2 plus, then we can use it to solve for other species. So that was what we talked about in the previous lecture. So if we go back to Excel, then we have the pH term, obviously. The first thing is to calculate carbonate concentration, because we need that later. And the carbonate concentration was from a closed system, total mass balance, alpha term could be used. Whatever we use, eventually we get that expression that is a pH dependent, also with combining other constants. So, but it's connected to pH. Once we have that, we can easily calculate bicarbonate and carbonic acid concentration. It's a very basic acid-base kind of expression. Now we have cadmium no precipitation, which is basically all the beta values, all the complexation, potential complexation. You see that on the top. Then we calculate cadmium max, which as you see is a relatively simple calculation, is less involved, but obviously we need to calculate the carbonate concentration first to get there. Once we have the two, the third one would be the actual cadmium concentration in the system. So cadmium 2 plus is the actual one, which is a very simple function. It's a min function, a minimum function between the two. So you have that also in the Excel, so it makes your life easier to minimum between these two columns. Once we have that, then the rest would be pretty straightforward. Cadmium, all the cadmium containing cadmium hydroxide species. And now we can calculate QSP. So QSP is, we can easily calculate it based on KSP, based on the concentration of cadmium and also the complexing agent, which in this case is carbonate. Then we can quickly compare QSP with the KSP. And this is color coded. The function of the color is basically comparing KSP versus QSP. If QSP is lower than KSP, it's green. If it's bigger, it's red. If it's lower, that means it's undersaturated. That means we can use the total mass balance. The mass balance of cadmium doesn't change. But when we get to oversaturated, basically we're losing cadmium through precipitation. And that's exactly what you see here. So as you see here, the edge of undersaturation is around pH of 3. And if you go back to the figure, the edge is basically pH 3 here. And then after that starts precipitating. And basically all the other complexation or all the species is changing based on what we had in the spreadsheet. So this would be just the only trick is to use that min-max function, and then the rest would be pretty straightforward. So here is the figure. As I mentioned, we have no precipitation zone. Then we start dealing with precipitation dissolution. So up to here we have precipitation, but after that starts dissolution. The main reason is that hydroxide is working as a complexing agent. So hydroxide is trying its best to bring cadmium to the solution. Carbonate is trying to take it to the solid phase, right? So there's a competition. And it seems the competition at higher pH is in favor of hydroxide, bringing it to the solution, which makes sense. We'll have more hydroxide, so it's trying its best to bring it to the solution. But if it was also precipitating with hydroxide, then this would just significantly go down. So that's sort of like a beautiful, delicate game of complexation versus precipitation that we can basically control an environmental chemical system to avoid or to accelerate a precipitation. So it could be a very cool way to do a separation also, if you're interested to do specifically do separation. So this one was cadmium, a very big environmental concern. The next example is lead. So let's see what's the difference between this example and the previous example. Obviously it's lead, so different equilibrium constant. So it seems based on the information that is given here without even reading the statement, I have 3 complexation, all beta 1. So it proceeds only to the first complexation, but with 3 different complexing agent, hydroxide, carbonate, and bicarbonate. And it seems I have only 1 precipitation, which is with carbonate. The last thing is, it seems the carbonate system, it's an open system. It's based on a gas-liquid equilibrium. So the source of carbonate is from the air. So I think that would be it, right? 10 to the minus 3 is the initial concentration of the lead. We have the partial pressure. We also have the Henry's constant. Now we just want to proceed. The first thing, as always, the diagram. So can someone help me with the diagram? PB2 plus. What is the complexation branch? So the first complexing agent is hydroxide forming PbOH plus, and it proceeds only with 1. And this is described by beta 1 hydroxide. What's the next? Carbonate? Yeah, but it's a different branch, exactly. So it is with a different complexing agent, CO3 2 minus, forming PbCO3. And this is beta 1 of CO3. And the last one, similarly, this is basically bicarbonate, forming PbHCO3 plus, and this is described by beta 1 of the carbonate system. So this would be the complexation part of the diagram. What else? Okay. With carbonate. Potential precipitation with carbonate. PbCO3. And then this would be KSP. Or the KSP that is given. Doesn't show that. And similarly, this CO3 is a part of acid base. Ka2, Ka1. So this would be precipitation. This is basically acid base. Any other branches? Any of the other species is connected to another species in a different phase? Okay. So which one of these species? One of the species. So when it comes to the gas-liquid equilibrium, it dictates the concentration of one of the species, and that concentration would be fixed. Which one is that? Yep, H2CO3. So the branch starts basically here. Only the concentration of H2CO3 is dictated by this new branch. So this is what dictates here. This part is HPM, and this is basically to CO2 gas. And this part is gas-liquid equilibrium. So we basically combine what we've learned in chapter 2 and chapter 3. So no matter how complex the problem is, we can easily break it down into this diagram. I think this would be very useful, again, to organize your thought, and it gives you a quick understanding of the speciation. The only branch that is left, it's basically having more complexes, for example, more than one. And also, this PB can also be in equilibrium with, for example, PB plus, which is basically the whole idea of chapter 4. Again, that makes it a little bit more comprehensive, not complex. As long as you can have like a very nice diagram, it would be very easy to use. So I came up with this diagram. I'm sure there are a lot of opportunities to improve it. I found this to be very useful for me, so I thought maybe this could be also good for you guys. But it's a nice approach to see how the chapters of the course are connected together. So now we can proceed with, as usual, like first, no precipitation. No precipitation scenario. We need to use the total PB. In this case is PB2 plus PB hydroxide plus PB carbonate plus PB bicarbonate. And once we have this one, we can basically rearrange it, use the equilibrium constant, the beta value, to get to the PB2 plus no precipitation expression. This would be the total PB divided 1 plus beta 1 hydroxide plus beta 1 CO3 beta 1 HCO3 also with precipitation. This was just similar to the previous case. PB2 plus max is the Ksp value divided by the complexing, the precipitating agent. So the minor difference between this example and the previous example is that to calculate both no precipitation and precipitation, we need to solve for carbonate acid base. Because in this case also, in addition to hydroxide, which is relatively easy to work with at different pH, these two we need to calculate. So we need a calculation of these two for no precipitation, also for precipitation. So we need to basically just do that simple calculation before we talk about no precipitation with precipitation scenarios. And we know how to do that. This time is for an open system. So we need to calculate for acid base open system. We know the concentration of H2CO3 is fixed, is a function of the partial pressure of CO2 and Henry's constant. Once we have that, we can calculate the concentration of other species. So bicarbonate in this case. And carbonate. We just rearranged a little bit to make it easier to work with. So now we can easily calculate the concentration of this guy as a function of pH and use it for either no precipitation scenario or with precipitation scenario. So similar to the previous case, we basically calculate PB2 plus, no precipitation, PB2 plus max, then minimum, then that would be our PB2 plus. Then we use that to calculate other species. So the only difference this time was we have more diversity on the complexation agent. instead of one complex, 4 different orders, we have 3 different complexes, which is proceeding with one ligand. And this time, the acid base is an open system, the difference. So we have difference compared to example 1. So if we go back to Excel, we see that this time, the first thing is H2CO3. It's connected to the partial pressure and also connected to the HPM. As you see, it's fixed, always fixed, because it's not a function of pH, it's a function of the partial pressure of CO2 and also the Henry's constant for CO2. Once we have this guy, we can calculate CO3 2 minus, which we needed for complexation, also for precipitation. Bicarbonate, we need it only for complexation. And again, min, max, then the minimum of the two. And then the following would be basically the rest of the calculation, doing QSP comparing with KSP to look at the precipitation profile. So here is basically what we get. So as you see, this time we only have precipitation, no dissolution. And we basically, it plateaus. And if you look at the value, this is basically very similar to 10 to the minus 7. Was it how much we had initially? Not really, it's 10 to the minus 3. So it seems we only can bring down the concentration of total lead in the solution up to this value. So beyond this would be not feasible, at least in this pH range, unless we introduce another precipitating agent to the system that takes the remaining lead concentration to the precipitation or to the solid phase. So again, this shows us up to pH 5, lead is in the solution. The dominant species of lead would be lead hydroxide, and then following by the bicarbonate and then the carbonate. Or sorry, the dominant would basically the lead itself. So this black line that we don't see it here overlaps with the total. So again, another PC-pH diagram that quickly tells us what's going on in the system and how the system would respond if we change the pH. But this time, behind the scene, much more is going on. We have so many things that are happening. Okay, so these 2 examples, we made it a little bit more comprehensive for the second one, but still, we're dealing with only one precipitation. But in reality, we might have more than one precipitate. So we might have, let's say, silver carbonate and silver hydroxide. So in reality, so we might get, let's say if this is a metal with L1, L2, and so on, it might also precipitate with L1, L2, and so on. So we want to see how we can solve for such system. The trick would be extremely straightforward. We used to calculate for the metal concentration in no precipitation scenario and the metal concentration max based on the precipitation. But now we have 2 max for precipitation with the first complex or precipitating agent, and then the max based on the second one. Now we take basically the minimum and we calculate other species as usual. So it's very intuitive. if we have silver in the system, it precipitates with, let's say, chloride and hydroxide. At every point that we're adding either chloride or hydroxide, we have to calculate the possibility of precipitation for either of the two. If one of them is checked, then that means we have precipitation. So that means out of the three, we take the minimum. So that's basically the explanation of why we're taking that minimum. The same thing we did actually for even one precipitation. So that was basically very similar. So the third example is taking into account more than one possible precipitation, for this time cadmium. Just looking at what is given, we can decode what might happen to cadmium. So it seems it complexes with hydroxide up to 4, given the beta value, with carbonate with 1, 2, with bicarbonate only with 1, and it could precipitate with either carbonate or hydroxide. So, and it seems it's a closed system. The total carbonate dissolve is fixed at 10 to the minus 2. Even it wasn't given like it's fixed 10 to the minus 2 compared to 10 to the minus 4, it's significantly bigger, so we could assume that it's fixed. But now it's just given that it's fixed. So the first thing is going with the diagram. What's the first branch? So hydroxide, how many? So the first complexing agent is hydroxide. It might form up to 4. So cadmium hydroxide plus beta 1 of hydroxide, cadmium with 2 hydroxide, cadmium with 3 hydroxide, and cadmium with 4 hydroxide. What else? Okay. How many? Exactly. So cadmium with 1 carbonate, beta 1 of CO3, and cadmium with 2 carbonate, beta 2. What else? Yeah, just the last one still in the complexation realm. So this would be cadmium HCO3 minus plus beta 1 of HCO3. So just make sure you have like a good understanding of like constructing such graph. It's very straightforward. So you'll see that in the homework, for sure in the exam. So just make sure that you include everything qualitatively and also quantitatively. So it seems this would be all the complexation. So what are the precipitation? So okay, nice. So hydroxide, well, that is really straightforward. So cadmium OH2 solid. This would be KSP of hydroxide. And then potentially with also CO3 2 minus, cadmium CO3, and then KSP of CO3. And similarly, this would be a part of acid base. And as mentioned, this is basically fixed. So we get the acid base, and we get the potential precipitation. So how many cadmium containing species we have? Seven. Why seven? Where is that eighth one? So these are the seven. And the last? Exactly. So this one. So eight. Eight, we're expecting eight. How many columns we're expecting for the Excel file? Yeah, somebody is looking at the next page. So just the species. We got 8 there, 9, 10, 11. So 11 species plus hydroxide and proton. So it would be 13 dissolved species, obviously more than that in terms of the columns, but 13 dissolved species by only introducing carbonate and cadmium to the system. So, okay, now we can proceed. First with no precipitation. And we can use the total cadmium. We are expecting 8 species to show up. Cadmium 2 plus, cadmium with 1 hydroxide, with 2, and 3, and 4. Also with carbonate and 2 carbonate. Also 1 related to the bicarbonate. Then we can calculate the concentration of cadmium 2 plus. Since this is a no precipitation, we can use this in P. Then it would be total cadmium divided by 1 plus beta 1 hydroxide OH minus beta 2 hydroxide beta 3 and beta 4. And the last one. Now we have with precipitation. This time we have 2, the cadmium 2 plus max, considering the precipitate with hydroxide, then this would be Ksp of hydroxide divided by the hydroxide concentration to the power of 2. That's basically literally coming from the Ksp expression. And the cadmium 2 plus concentration, max, considering CO3, Ksp CO3, then CO3 2 minus. So now we need to calculate the concentration of carbonate at different pH for this given system. Well, very similar to the first example. It's a closed system, so we can use the total mass balance. And we can basically calculate that as a function of pH. But when we look at the closed system, so we assume that it's a closed system. In reality, carbonate system is not a closed system because we might get some precipitate, carbonate containing precipitate. So then we get the total CO3 to be H2CO3 plus HCO3 minus plus CO3 2 minus. Is it the only, are these the only species containing carbonate in the solution? Yep, some of them could complex also with cadmium. So plus cadmium CO3 plus 2 times cadmium CO3 2 plus cadmium HCO3 plus. This is 2 minus. So as you see, this is a little bit involved to calculate it, but we can make a very logical assumption and basically ignore this part. The reason is that the concentration of cadmium compared to total CO3 is significantly lower. So even if all the cadmium would complex with this species, still this fraction would be much bigger on the total mass balance. So that can be ignored. Once we have these three, then it would be similar to example 1, how we did for a closed system. Again, you can use alpha, or you could use what I did, for example, to just rearrange it in a way that you can get to the concentration of one of the species as a function of pH and constant. Then this would be similar to example 1. So what we do is basically we calculate CO2 species, which is basically an acid base. Then we calculate the cadmium 2 plus concentration, no precipitation, cadmium 2 plus max with hydroxide, and cadmium 2 plus max CO3. Then we take the minimum. That would be our cadmium concentration. Then we solve for other species. So the only difference here this time is that instead of minimum function between the two, we're taking minimum between 3. So the reason we ignored this basically because the total CO3 is much bigger than the total cadmium. So now if we go back to Excel, this time the Excel file is basically a little bit longer. We have complexation reactions, different types of complexation, 2 different precipitation, and then we have acid-base for a closed system. Here, as I mentioned, first we calculate for acid-base system as a function of pH. Very straightforward based on chapter 2. Then the no precipitation, as you see on the formula, is just longer, more comprehensive. Then the max for carbonate, so it's obviously related to the concentration of carbonate. Then hydroxide, max based on the hydroxide concentration. Then we take the minimum between the 3. Once we have the minimum, then it would be the concentration of other complexes based on the beta value. Then this time we have 2 QSP, one for carbonate containing precipitates, the other one is for hydroxide, and then basically we can compare it with the KSP of the individual KSP to see whether this is undersaturated or oversaturated. And this would be something like this one, that in one side it's showing the carbonate precipitate, and this one is talking about possibility of hydroxide containing precipitate. But eventually what we get is basically this one as a total concentration of cadmium in the system, which is basically a combination of both phenomena that is happening behind the scene. A part of it is, for example, here, both precipitation is happening. Here is just one precipitation is happening. So it's the result, the net result would be the profile would be like this one, which the shape is a bit weird is because the system behind the scene more is happening. And all the individual species, we can basically describe why the trend is like this. For example, for this one, because it's all about the competition of the complexing agent, whether it's participating in the complexation reaction and precipitation. So many things are happening behind the scene. Just this would be the total cadmium concentration in your system. So if you do, for example, ICP, this is the value you get at pH 7, combining all the species together. So to wrap up what we talked about, here we basically what we did was similar to the previous lecture. We highlighted the complexation reaction, potential complexation reaction. We also highlighted the precipitation or precipitations. And then we mentioned that this precipitation agent could be a part of acid base, which could be a closed system or an open system. And the corresponding PC-pH diagram, we talked about that. If you remember in chapter 2, we started with a figure that had 5 lines. Now we're getting more than 10 lines, so it's getting more and more comprehensive. It gives us a better understanding of what could happen thermodynamically speaking in the system at equilibrium. Would it happen? That's a different question. That's all about the kinetic. So as I mentioned in the next lecture, we're going to talk about redox chemistry.